Hello, so in this video we will talk about unit vectors, especially we will see how unit vectors in rectangular, cylindrical and spherical coordinates are represented. So let's start with the definition as usual. So if we have a space which has n dimensions, we will say the kth unit vector will be denoted by ek, and it is a vector with two properties, that its magnitude is 1 and its direction is in the kth direction, okay, and all, such that all values in other dimensions except kth dimension remain constant. So we'll see what it means. I mean, I think it's the first part is clear enough, but for the second part we need to see some examples to know what it means. So then let's now see. So now this is a unit vector in the z direction. So then our second statement said that the x and y, so you can see that from here to here my x and y are not changing, only my z is changing. So then my xy point is still this one at the xy coordinate, it's still the same, but only the z value is changing. So this is what I'm trying to say. What we are trying to say is that all the other dimensions, they are constant. They're not necessarily zero, they are constant. So this means if we represent it in I, j and k, e of z, so ez, this is equal to 0 I plus 0 j plus 1 k, or we can just say k here. So similarly, e of x is equal to I, and e of y, this is equal to just j. Okay, so this is what it means, that we have the direction is only in the kth direction and the magnitude is 1. Okay, now what does it mean to have unit vectors in cylindrical and spherical coordinates? So let's see. Now we are talking about cylindrical coordinates. So as I recall, so cylindrical coordinates, a point is represented by r, theta and z. Okay, so then we are interested in e of r here. So now we are seeing the top view or the xy plane here. So you can see that the r vector is, so this is my origin here. So this is, you can see that only the r is changing. So then in this state only the r is changing. My z is not changing because I'm still in the xy plane, and my theta is not changing because this theta is still the same in the whole of this line. Okay, so this is my theta. Now we are interested in what is this e of r in I, j and k. Now this is easy because this is in direction, so the x component is cos theta and y component is sine of theta. Okay, but then since we are talking about I, j and k, so we need to, it's better to write cos theta as x over x squared plus y squared, I plus y over x squared plus y squared, j. Okay, so this is my e of r. Now we move on to e of theta here. So this is my unit vector e of theta. And now what does it mean? So this is the top view, or this is the xy plane here. So this means that, let's say this is my origin here, and then this is my r is not changing, only theta is changing. So then this means this will be the tangent of this. So at any point this vector, this e of theta, this is equal to tangent to the radius, where radius is this guy, or I can just say r, where uh, on a circle with radius r. Okay, so what I'm trying to say is that this is the circle, the green circle you are seeing. You don't see it exact circle because this is the scale is slightly skewed. So that's why we see the slightly elliptical shape here, but this is a circle here. So we are talking about this vector. Okay, now if I now remove this, let's say, now we are interested in the angle it makes, right? So then again we see that this is 90 degree. So then this means that if this is theta, then if I bring it here, then this angle will be 90 minus theta. Okay, and the x component will be in the negative x direction. So we will have minus cosine of 90 minus theta I plus, and then y direction is up, so I can say sine of 90 minus theta j. And what is the z direction? Z direction, theta is only always measured within the xy plane, so plus 0. So I can also say it minus sine of theta I plus cos of theta j. So again I can write it as minus y I plus x j times 1 over x squared plus y squared. Okay, so this is my E of theta. Okay, let's move on to spherical coordinates now. So for spherical coordinates, we have, as a recap, a point is represented by rho, theta, and phi. Okay, and rho is what? Rho is, we know that, r squared plus z squared square root, and theta is angle uh, between z-axis and rho, and rho is the radius of the sphere. Okay. Okay. Now we are interested in E of rho. Okay. So then we know that E of rho should be, because this is its as x component is just x over rho. Its y component is y over rho, and its z component is z over rho. Okay, and then I can also say that xi plus yj plus zk divided by x squared plus y squared plus z squared, because this is my rho. Okay. Okay. Now we go to E of phi. So E of phi, so we will break it down in such that we will first of all talk about z component. So now if you see this picture here, so this is the top view. So top view, if we see the top, if we see it from the top, we will see just one line, and if we see it from the front, so this is my tilted ring. So tilted, this is tilted by angle of, so this tilt is by theta, because you see this is your theta here. It's your theta. Okay, and then if I see this triangle, this is my rho, this is my r, this is my z, and this is my theta. So then now you can note that this is the same relationship which we used between to find E of theta and r in the previous case. So in other words, what we are trying to say is that the z component is just a cosine of 90 minus phi, which is also equal to sine of phi. But it's a negative direction. Why? Because you can see that it's going down. This is if you are doing it this way, then this is positive, but xy component will be negative. Okay, so that's fine. So this is my z component. Now if the z component is sine of phi, I should remove it. So if z component is sine of phi, then xy plane component will be cosine of phi. Okay, and then x component is just cosine of theta cosine of phi, and y component, this is equal to sine of theta cosine of phi. Okay, so my representation is cos theta cos phi I plus, or if we are talking about this plus, then this is minus here. So then minus sine theta cosine of phi j, and plus sine of phi k. Okay, and then if we write it in xy coordinates, then I can write it as x over x squared plus y squared. I can write it as, so this is cosine of phi, so this I should write it phi, sorry. So cosine of phi is z over, so z over x squared plus y squared plus z squared. So similarly I can put y over x squared plus y squared z over, and this is a minus here, x squared plus y squared plus z squared, and then I will say j here, and then I'll say plus x squared plus y squared over x squared plus y squared plus z squared. Okay, so this is my expression for this is my E of phi. Okay, now you can also, since they are unit vectors and they should be orthogonal, so then this means that if you do E of phi dot product with E of rho, you should get 0, and this you can check easily whether this is the case or not. And similarly, E of phi dot product of E of theta should also be 0, and vice, and for E of theta times E of theta dot product of with E of rho also should be 0. Okay, so here we try to explain the concept of unit vectors in spherical coordinates, cylindrical coordinates, and rectangular coordinates. So hope it was easy to understand, and thanks for watching. Hope you like the video.